This morning, we are very honored to have Professor Peng Jong-Shi to give two distinguished lectures. So let me give a brief introduction of Peng Jong-Shi. Actually, in fact, maybe it's redundant, but I think for the students, I think it's still necessary. So Professor Peng Jong-Shi is currently the Epstein Family Chair and Professor of Industrial and Systems Engineering at the University of Southern California. He was the Caterpillar Professor and the head of Department of Industrial and Enterprise Systems Engineering at the University of Illinois at Urbana-Champaign from 2007 to 2013. Prior to that, he was the Margaret Darin Professor of Applied Mathematics at Rensselaer Polytechnic Universities from 2003 to 2007. Professor Pang received the John Monument Theory Prize in 2019, the Frederick Lancaster Prize in 1994, both awarded by the Institute for Operational Research and Management Science, and the George B. Danzig Prize in 2013, awarded jointly by the Society for Industrial and Applied Mathematics and the Mathematical Optimization Society. Professor Pang is a member of the SIME 2019 class of Fellow of SIME and an elected Fellow of Informs in 2019. He was elected as a member of the National Academy of Engineering in 2021. So his research interests include the mathematical modeling and analysis of optimization problems, game theoretic problems, and equilibrium programs, and there are many applications in diverse disciplines. He has recently written a very thick book on non-problems. All right, so I think without further ado, let's welcome Professor Pang to give his first distinguished lectures on non-convex stochastic programming.
Hello. Okay. So usually I do this at the end of the conference, but because one of the organizers is leaving soon, so I'm going to do this right at this point. So personally, and also on behalf of the the participants, really want to express a deep gratitude to the three organizers, and I encourage Defong and Kim Chuan and Steve, and I suggest that we all give them a round of applause before Defong sort of goes away. Okay, so thank you, the three of you. Right, so it's always a pleasure to visit Singapore, and I've been here for several times, and this is my first time. As Defong point out, this is my first time giving an online, in-person lecture after 3 years. So this is particularly exciting, right? So, so thank you again. I really enjoyed good food, good talk, and the talks are just wonderful. I learned a lot. It's just amazing to see how sort of vibrant our field of optimization has become. It's just seeing so many sort of young faces, because you guys are the future. We are the so-called the old dinosaurs, right? So passé, but then it's good to see all the young faces. You guys are really the future of our field. So as I said, I learned a lot from the talks. I was here also last week, part of it, and so I actually learned a lot from the two workshops. And I'm really impressed by the talks. But today my topic is a little bit different. Okay, and you may say that this is probably not a very popular topic at the present time. But I hope that this will grow. Right, so I hope that this will grow. And in particular, I'm going to talk about. Well, I think that you all know about stochastic programming. What you may not have seen a lot is the case when these stochastic programs are non-convex. Okay, and this is very difficult, as we heard from Anthony's talk yesterday. Non-problems are already hard. Non-deterministic problems are already hard. But if you really want to treat stochastic programs, especially with non-convexity and non-differentiability, they become even much harder, right? Much more harder. And so now it's natural for you to ask, why do I want to do something like this, right? I'm asking for trouble. because they are really tough. But I think that this is necessary. I think that because my perspective is that, I mean, you probably will agree with me that a lot of the so-called real-world problems are non-convex at the very bottom of the real formulation, right? And so I think that it's necessary to really sort of engage in trying to understand a bit more about non-convexity with uncertainty, and that's where the stochastic part comes in. So what am I doing today? So I'm going to have two parts. The first part is that the first 20 minutes, I hope it's actually a little bit easy and comprehensible for all of you. But then the later part probably can become a little bit technical. Okay, and so I try to do a good job giving you the big ideas, right? So what are the major ideas involved, rather than really going to the sort of dive deeply into the big ocean. I think that's too much. So although I'll give some details, but then I think that the focus of the talk is mainly on the main ideas. So the two talks. First one, I'm going to introduce the problem, talk a little bit, and then talk about two special classes of non-convex SP to give you a bit of insights of how some of the ideas can be applied. Right. So, although at the beginning I would pose the problem with general sort of possibly non-convex constraints, but then essentially we have convex constraints, and that makes the situation a little bit easier. And then the second talk, I'll focus mainly on change constraints. I mean, change constraint problems are probably the most difficult, definitely one of the most difficult class of optimization problems. Of course, there's a lot of study on the change constraint problems, but I'm hoping to go further. Now, let me go back. The phone is still here. Good. I would not have been able to do this work if not for the two co-authors, right? So Dr. Ying Choi was a former student of the phone who's ignoring her, just looking away. And then, of course, she was the postdoc of Kim Chuan. Right? So, and she spent a couple years with me, and we did a lot of work together. And then the other collaborator is Jun-Yi, who's exceptionally good, well-trained in stochastic program, and I really have benefited greatly from her interest in stochastic and her expertise in stochastic programming. Right? And so she's now at Tsinghua, and so if you have a chance, do visit her, and or get in touch with her, and maybe some collaboration with her would be good. Right? So I really benefited from the expertise of these two young colleagues. Right? So they are Ying is intimately related to Singapore. Right, so having the great pedagogy from two of our leaders, and then Jun-Yi is really a rising star in the stochastic programming area. Okay, so a lot of talks. So what we are doing is really taking baby steps. Okay, taking baby steps, and you can see that there are a lot of things that you can question why we are doing this and how, and can we improve on the results. And the answer is yes. So we are, in fact, just taking an initial scratch at some of the challenging problems in the talk. So we are basically just taking baby steps, right? Baby steps in this area, which we think that is really a new area of stochastic programming. Right? And I will give you explain why I consider this as a new area, because there's really a lot of details that the traditional stochastic programming really has not dealt with. Now, I used to put the Big Bang in red, and some of you probably know what that means, especially those from the US. Do you know why the Big Bang?
I don't know why it's in red.
Okay, well, the Big Bang theory is my favorite sitcom. Okay, who knows about Big Bang theory? Okay, you know about Big Bang Theory, right? You don't know Big Bang Theory? Anyway. Yeah, okay. Anyway, so the Big Bang Theory is my favorite. My favorite sitcom. Right? So those who have not seen, watch it. I suggest that you watch it a few episodes. So anyway, so I thought that I used my favorite term, and this is what my hope is. That is ultimately we're taking baby steps now, and ultimately this could become the foundation to this area of non-convex stochastic programming. Okay, now so give you a background of this non-convex stochastic programming. Traditionally, stochastic programs, of course, have a long history, right? So starting in the 50s from Danzig and others, but mostly it was studied under the umbrella of convex programming, right? Then, of course, there's nothing wrong with that because convex programming is so powerful, and exploiting the tools and theory of convex programming, of course, is a natural thing to do. And so it really has been studied, especially from the computational aspects, right? So if you look at how stochastic programs are solved today, and you will see that I would say that 80-90% of the time, the focus is on solving stochastic linear programs. And even in this context of stochastic linear programs, you will see, I'll show you that the framework is still very restricted, right? So that's one motivation. It's natural to ask, why do people not so much look beyond the stochastic linear program or sort of try to extend the tools of convex programming? Now, mind you, ultimately, when we're going to solve this kind of non-convex stochastic programs, we still rely on convex programming, right? So all the things that we have heard in this workshop, they certainly are the foundation to what we are going to do here. However, there's a major difference because we don't start with a convex problem. And so therefore, ultimately, we're going to build machinery that is based on convex programming, but we go further, right? So you need to go just further than just posing the problem as one convex program and then use convex programming methods. We need to go further, right? But we still rely on convex programming. There's no doubt about it. But the models themselves are not convex. So what's wrong with this convex programming based sort of direct, straightforward convex programming base? The drawback that we see it is that invariably you're working with convex models, and then you hope that your convex models represent the physical problem well, right? And so and now that's the question: is it always the case, right? So is your convex programming model really the best thing that you can do with respect to solving a realistic problem? So this popular approach comes at the expense of model faithfulness. That's what I said. Is your model really the most faithful description of the physical problem that you are interested in? So our research focus on an opposite direction. So we are prioritizing, model faithfulness, ahead of solution methodology, right? So we want a model to be sort of faithfully describe the physical problem, and they may not be convex, but then we try to do the best we can to deal with that presumably more faithful model of the problem. So we're taking this opposite direction, that we prioritize the modeling part, right? That we get really a better description of the physical problem. So hopefully the benefits of this contrarian approach, right? So you can tell that I'm a contrarian because I'm sort of looking at non-convex problems. Benefits of this contrarian approach is that hopefully we can enhance the modeling of the physical problems, right? Give a better description. And then the sort of intellectually, this requires us to think beyond convexity. And this really leads us to a lot of, Anthony yesterday mentioned about variational analysis. That already is one step beyond convex analysis, right? So it requires us to sort of look at things that are traditionally not available, right? So leading to new theory and methodology, and therefore give us a broader, extending the boundary of the of optimization. So, and then of course, at the end of the day, we're hoping that this non-convex framework will offer the likelihood, right? I'm not saying that for sure, but because you give a better description, then hopefully there's a better chance that the solution that you obtain, even though they are not optimal in any sense, but hopefully they still give you improved solution because the model is a better description of reality. So anyway, so those are the forwards. And then, of course, we are going to build on the advances in modern deterministic non-problems, non-optimization. And many of you, or all of you probably know about this book. And so hopefully we're going to build on methods, techniques that we summarize in this book and beyond. Right? So this was, surprisingly, this is almost 1 year since the book has been published. Surprisingly fast. And again, I should thank two people in this audience who are very supportive of this project, right? So I'm looking on my right-hand side. I'm also looking at my left-hand side. So they are very supportive of the project and can get of this book and get this book accepted for publication. So thank you, right and left. Okay, anyway, so I hope that you find, if you already have a copy of the book, I should warn you, okay, there's a goal of this book. So the book is about 700 some pages, right? So I would be very happy if at the end the number of pages in the errata, right, will not exceed 10 pages. Right? If that is the case, I'll be very happy. I can tell you that right now the number of pages in the errata still stays at 2, right? So I still have some way to go beyond my hope, right? So 10 pages of errata for a 700-page book is okay, right? So be kind when you read the book and find that there are mistakes. There are already some mistakes in the book. Okay. Anyway, so now I want to give you the formulation. Now I hope that you will not be scared because. Well, on the one hand, you may be scared. On the other hand, you may not be. Okay, so this is a problem that we want to study, right? So you have a expectation. You can have deterministic functions there. You can absorb the deterministic functions within the expectation. So you have an expectation objective, but then you have expectation constraints. And what is described below is standard formalism of the problem. But I do want to point out that you have expectation constraints here, and then you have deterministic constraints. And for our purpose, we're going to take the deterministic constraints as linear, okay, just for simplicity. So you have deterministic linear constraints, and then you have a set of expectation constraints. Okay, the way this is written here, you say that, oh, this is nothing. This is just a standard stochastic program, and so why do I make a big deal out of it, right? Standard stochastic program, expectation objective, expectation constraints. Okay, now what is not traditional about this is that we permit the functions to be non-functions, right? So you have those CKs are the functions within the expectation. They need not be convex. They need not be differentiable. And even more so, they may not even be continuous. Right? So you have non-convexity, non-differentiability, and non-continuous, discontinuous. Okay, so those are all absorbed in the functions. And that's a new aspect of, and of course, when you allow this, then really now your constraints can be nasty, very nasty. Okay, and I'll show you later. So what's our goal, right? So that's the basic framework. So I hope that one thing that you get out from this talk, if not for the later details, at least you know what we are aiming at. We're aiming to study this class of problems where you have expectation functions, but then the functionals within, the random functionals within those expectations are non-functions, okay? Possibly even discontinuous. So we hope to develop a comprehensive theory. So think about this. When you try to compute a solution of this problem, what do you mean by solution? Global is out of the question in this setting here. And, right, so what kind of solutions can you expect to be able to compute? Okay, so that's the first question, right? So this would be like some kind of computable solutions that are necessary. Right? Stationary solutions are really, the stationarity conditions are really necessary conditions for local optimality. And so we try to, you have the set of local mean here, and we go a little further, we get into the stationary solutions. Okay? But even stationary solutions, because of this setting here, is not clear what is really meant by a stationary solution. And so we try to provide we have extensive understanding of stationary solutions in the context of deterministic non-optimization problems. Okay? We have a very good understanding of that. But then when you have this kind of those non-functions embedded in an expectation function, that's not well understood. And of course, we want to be able to compute, right? So we want to also develop effective solution methods for computing those stationary solutions, which I have not told you about. Okay, so the goal is fairly ambitious, but keep in mind, I want to emphasize the word baby steps, okay? Because it's very difficult, but then we hope that our baby steps will eventually pay off. So again, this is a big picture idea of what the kind of methodology we're going to use, right? So the first one, because you have discontinuity here, we allow functions to be discontinuous. So the first thing you want to do is to do some approximations of this discontinuity, right? And so that's the first kind of approximations, which we call functional approximation. You want to approximate, at least turn those discontinuity, remove them. And so what you're going to get is that this is my original function, and you're going to sort of use some kind of approximation. Notice that I do not use the word smoothing. Okay? Smoothing is only one way to try to approximate things. So we're saying using the broader concept of just approximation. Okay? And you see some approximation, and you can think of them as, smoothing. But then the smoothing part, usually you associate smoothing as saying that the smooth functions will be, the resulting approximation function will be differentiable. Okay? Over here, you see that some of the approximations will not be differentiable. Okay? So here you have a delta, and the delta really is the accuracy measure of your approximation. Okay? So that's the first level. The first thing we need to do is that we need to approximate the discontinuity. The second thing is that you have the expectation, right? And so in order to be able to solve problems involving expectation, we need to discretize, right? We need to take samples would be one thing, right? So in particular, we've been using this sample average approximation, SAA. Now, some of you may say that why not use stochastic approximation, SA methods? Well, our favorite is SAA, stochastic approximation. So you take samples, right? You have samples here, and then you replace the expectation by this finite sum. So that's the second layer of approximation. You have functional approximation, and then you have approximation of the expectation operator. Okay? And then now you approximate this, so your functions, with the delta there, your function becomes possibly smooth. Okay? But then I don't want to solve non-convex subproblems. Right? And so now I need to go to the third layer, right, where I actually approximate, try to come up with convex approximation. All right, convex surrogates. I call them surrogate functions. That's a surrogation idea, is that you replace those non-convex functions with the delta there by some approximation. The most standard one would be the majorization approach, right? So some of you, this is very standard now, and so that would be one possible surrogation functions, but there are many. I mean, the idea of surrogation function really encompasses all the, encompass all everything basically we do. So we basically lump this idea of how to actually do the computation under this umbrella of surrogation. So we're going to solve a sequence of surrogated subproblems, and each one of those surrogated problems, I can compute the global mean of those subproblems. So that's the third idea. You do a functional approximation, expectation, replaced by sample, average, and then do a surrogation so that I can actually solve the subproblems in practice, okay, to global optimality if desired. Otherwise, basically, you're going to get some kind related to convex programs, not necessarily convex, but you can get global mean of those problems. Okay, so the last thing is that we have nasty constraints. Right? We have nasty constraints. How do we deal with those nasty constraints? Well, one standard way, one typical way, is that we use some kind of penalization. Okay, you penalize the constraints and put them in the objective. Right? Now, what we are interested in is that we are interested in exact penalization, so that your parameter does not need to go to infinity. Okay? So these are the four basic approaches that we use to try to deal with this. And now you need to put everything together. Okay? So this is a high level thing. So this is the first step, all right? So in this step, I'm not doing anything with the expectation. I already have a delta here. So in other words, this already involves, has taken care of the first, for the functional approximation, right? So I penalize the constraint using the, you can use any favorite residual function that you want, but here we simply take a very simple minded constraint residual, right? Which is the max of the violation, constraint violation with 0. And then the putting all this together, so then we get the penalization term. And then you can see that there's a parameter rho here. So this is a penalized version of the original problem without doing anything, just penalizing it. There's no theory involved so far, right? But interestingly, and this of course is a trivial observation, that this problem is equivalent to this problem where you basically relax the constraint. You put it, instead of less than or equal to 0, you put it less than or equal to gamma. And then you minimize the sum of the penalization. Okay? So what this serves, this is penalization, but you can look at it also as a constraint relaxation. You keep the constraints, but instead of making it less than or equal to 0, make it a gamma, and then you minimize that gamma. The two formulations are equivalent. Okay? So that's the first kind of the first level, also the approach that we use to deal with the nasty constraints, penalization. And I just want to point out that constraint penalization is closely related, if not equivalent to constraint relaxation. Now, even at this point, you need to be careful. Okay, you need to be careful because from the perspective of optimal solutions, the constraint relaxation is very easily seen to be equivalent to the original problem. Okay, but then because the problems here are not convex, You cannot compute the global minimizers of these problems. And so the question is whether stationary solutions of these penalized problems are equivalent to some kind of stationary solutions of the original problem. Okay? So that's something that I'm saying that when you talk about optimal solutions, the equivalence is fairly easy to see. But then when you go deeper and look at, instead of global solutions, you look at stationary solutions, then the equivalence of stationary solutions is not immediate. I'm not saying that's hard, but it's not immediate. Not as immediate as the case of global mean. Okay? So that's the first formulation. The second thing we do is that now we introduce surrogation. Right? So we replace the delta function. Okay? There's no surrogation here. Okay? We replace them by surrogation at a given point. Okay? At a given point, we're going to surrogate the objective. So now you see the head here, and then there's a reference point. There's a reference point where we do the surrogation. And then, again, this is equivalent to that. So the second family, the original family, the original family is just penalization, just penalizing the difficult constraints. And then now we do surrogation. And then presumably you're going to get something nicer about for this problem in terms of computation. Okay? But again, I haven't done anything with the expectation. Okay, so now you get to what I call the computational workhorse. This is what you do computation. Is that you surrogate, and then you sample. Okay, and then ultimately you're going to get either this problem or that problem. Now you see that I have the sampling here. Okay, and then this, of course, is this. And this subproblem here, okay, is the one that I'm going to solve. Okay, and the idea here is that the surrogation is such that this problem at the end can be solved globally. Okay, can be solved globally. So I go through and then I'm going to iterate. Right. So you have a reference point here, x bar. Okay, and then x bar is going to be replaced by the new point. So this is step-by-step deduction of the ultimate subproblems that we're going to solve. Is this one, right? So this is one. It involves approximation, function approximation, surrogation, and then sampling. Okay. So big picture is just a big picture. Of course, the devil is in the details, right? How this actually works. So before I do that, I want to show you why we should look, why we are interested in this kind of sort of non-functions. So let me start with this. By now it's actually a few years old. This concept of piecewise regression. Okay, piecewise regression. Now, you're all familiar with linear regression. The underlying linear regression is that you have a linear statistical model. Okay, but linear statistical model in a way is very restrictive, as we all know. And so there are, of course, other methods to sort of expand the statistical model. And one such generalization of a linear model is a piecewise linear model. Okay, so this would be an example, right? And this, of course, Mehdi is very familiar with this, and I'm sure others, is this kind of in the phase retrieval domain, the underlying statistical model is really the absolute value or modulus of this. Okay, so now you get into something which is not linear. Right? The statistical model itself is not linear. Okay, but most generally, every piecewise affine function can be written in this form: max of finitely many affine functions minus max of finitely many affine functions. Every piecewise affine function can be written in this form. And so now the parameters that we want to estimate, the C is the input, okay, and so that we're going to substitute those by data or samples, and then the variables to be estimated are the A's, the alphas. Those are the slopes. A's are like the slopes. The alphas are like the intercepts, right? So, but then we have two terms. We have max minus max. Okay, so this is the most general form. Now, in this case, for example, of course, we don't have the second max because this function is convex in X. right? But then most generally, a piecewise affine function would be of this form. And then the parameters to be estimated would be the slopes, the intercepts. Now, why do you think that this is better than linear approximation, linear model? Well, imagine that your data, okay, is not my favorite letter, capital M, big M, right? Your data is somewhere around the big M. Now, if you use a linear statistical model, you can never recover the data, which is like a big M, because big M is, of course, piecewise linear. So if I allow myself to use a piecewise linear model as the underlying model, there's good chance that I can recover the big M letter. So that gives you one reason why piecewise. In fact, this idea it did not come from us. It comes from some statisticians. Okay, so we have a paper on this published in Science, talking about the least square using a least squares error function, right? And then try to use this in a statistical in statistical estimation regression. Of course, we heard about the ReLU activator in deep learning, and so this is a two-layer. We've seen this in one of the talks. This will be a two-layer neural net with ReLU activation, and then this is, of course, another example. It's piecewise linear. There are more. Okay, so but then so in this case, what we get is that we get something which is not. It's continuous, but it's not differentiable. The model itself, the statistical model in terms of the parameter x, is not differentiable. And the optimization problem is this one. Expectation of this will be the output, output the data, for example, and then the input to the model. And then there's a deviation function, loss function, and we want to optimize over the parameters. Okay, so that would be the first example of a non-convex statistical stochastic program. Okay, I don't have a lot of time for I think I've only until another maybe 10 minutes or so. Discontinuous functions. Okay, how do discontinuous functions come about? This one, most of you, or I bet all of you know about this. This is the sparsity function, right? In sparsity optimization, is 0 if the t is 0 is not 0, when t is not is 1. So this is the counting function, right? If the number is 0, then it's counted 0. If it's not 0, it's counted as 1. Okay, so that's a function that is very common in sparsity optimization, the L0 function. Now, the other way is the so-called the Heaviside function, something that I learned when I was in my undergrad. The Heaviside function is constantly equal to 1 on the right-hand side, my right-hand side, and then is equal to 0 on the left-hand side. But there's a discontinuity. There's a discontinuity at 0. Okay, there's a discontinuity at 0. So this is very useful to express probability function in terms of expectation function. So here's a probability function, right? So I want to, x is a decision variable, and the decision variable satisfies, for example, the constraint that the probability of this thing is less than or equal to something, for example. I want to optimize this. So this kind of function can be in the constraints or it can be in the objective. Okay? And so when you have this kind of function, this is a probability function. This is how you get what people usually do when dealing with change constraints. They convert the probability functions into expectation functions. So this is very easy. It's greater than or equal to 0. So, and then I use the indicator function. This is the closed, and this is the indicator function composed with this z function. And then it's very easy to see that the probability of this event is actually equal to the expectation of this composite function. And now you see the Heaviside function appearing inside the expectation. Okay, and now suppose you want to optimize this thing, how to do. So this is this kind of a conversion is You find it in all the literature on chain constraints, dealing with probability functions. This will be a decision function. It's just a straightforward generalization where you have an outcome. So basically what the context that this appears is that you have a decision rule. Okay, you have a score function, so to speak, or decision function. And if this score is non-negative, then this is the award or reward that you get. Okay, so this is you can think of this as the A is the outcome if the score is non-negative. Okay, so and this is used a lot in classification, except that now is that there's a reward associated with the correct diagnosis, for example. Right? So this is the score function of the random event, and if the score function is non-negative, then this is the event that you get. Right? So now again you have this, but this is a easy generalization of that. But what is not so trivial is to have the inner function is that your reward is decision dependent. Okay, so now you have a function phi here times this indicator function, and this is something that we want to optimize. Right? We want to optimize. So now we need to deal with. Now over here again, I have not specified any properties of the functions, and in general they can be quite nasty too. But even if the outcome or reward function is nice, you still have this indicator function that you need to deal with. Okay. Fractional expectation functions, right? So you don't see this a lot in the stochastic programming literature. I want to optimize a conditional expectation. Okay? Or you optimize or constrain a conditional probability constraint. Okay? So there's a decision variable, but the objective or constraint function is a conditional expectation, conditional probability, and you want to optimize that. You don't see this a lot in the literature, unfortunately. To me, I think that's a good reason. Okay? And the reason is that typically these kind of functions are nasty. They're not convex, for one thing. Okay? But then again, if you have this kind of conditional expectation or conditional probability is easy. Is that it's just a joint event and then divide by the probability of the event of the condition being satisfied. So now what you see here in the numerator, this is the conditional probability, is that you have a conjunctive event. Right? So the numerator is the probability of this event happening and this event happening. Okay? And so now how do you do that? Well, so one way to express this kind of conjunction, this event and this event, this less than or equal to 0 and that less than or equal to 0, is to say that the max of the two less than or equal to 0. Right? The max of this and that less than or equal to 0 is the same thing as the first one is less than or equal to the second one is less than or equal to 0. So now you see this max operator. Right? So even though these functions may be nice, may be smooth, may be linear, but then once you have this kind of a conjunction, I want the two events to happen at the same time. I want the probability of that. Right? And so now immediately you get this kind of a non-differentiable function, but then that is embedded in. That's embedded in this Heaviside function, this indicator function. And think about try to optimize this. And you also, moreover, you have a denominator that involves also a probability function. So this is optimizing or constraining probability, okay, or conditional probability. Okay, moving something back to the maybe risk literature, you see a lot of so-called deviation functions. The standard one is the variance, right? So the variance is the deviation from the mean. Deviation from the mean, and this is a variance. Now, people always say that this is convex, but that's only true when this random function is linear in x. When this function, this random variable, is a nonlinear function in the decision variable x, the variance itself need not be convex. Okay, only when this function is a linear function, then yes, the variance is a convex function in X. As soon as you move away from the linearity of the Z function, your variance function may not be convex in X. Furthermore, standard deviation, definitely not convex. Okay? And then you can also have this kind of absolute so-called semi-deviation and also absolute. So these are all deviation with respect to the mean. Okay? And these functions, although they are very common, but then the thing that you see that will give you convexity is the fact that you have a linear random functional. As soon as you move away from the linearity of that Z function, the convexity of this kind of deviation functions is lost. More generally, you can tell Mark, okay? His name is here, okay? So Mark is his academic father, and Ben Tao is his academic grandfather, right? So their names are here. Is that they? I can tell you stories about them, right? So, and I learned a lot from them, right? So this is one thing. I mean, I was talking about something else, and Mark was in the audience. He stood up and raised his hand. Jong-Shi, do you know about these papers of mine? Right? And of course, I did not know. Right? So, but then from then on, and actually this concept of optimized certainty equivalent was introduced in Mark's PhD thesis. Okay, and I didn't know that. Right? So this is one benefit of going to conferences. He corrected me, and now every time I talk about this kind of risk, this actually came out. So what is this? The so-called the optimized certainty. I need to stop. Okay, so I'm actually only at a third. This is almost the time. You have this so-called the optimized certainty equivalent. Is that there is a utility function. Okay, there's a function v here, extended value possibly, and then that is defined. So you have your u function here, and it's defined as the minimum value of this one-dimensional optimization. So you have the variable to be optimized is t. You have that utility function. That's the v usually. V is actually in this context is a negative of a utility function. And the minimum value of that, okay, is defined as the OCE base, which is the optimized certainty equivalent. So it's deviation because I'm subtracting from the mean, okay? But then I don't take the expectation outside. Instead, I take a risk measure, which is given by this OCE to define the deviation, okay? So now what you see here is that this function, so I'm going to, if I substitute this in this function itself is a stochastic value function. Okay, it's a value function because it's the minimum of an optimization of an optimization problem, but involves the expectation inside. Okay, so this is a stochastic value function. Okay, that's the OC. Now this is OC-based deviation. One more and then I'll stop. Two more actually. So the use of that. Okay, so I want to mention about this. Okay, so I mentioned the CVAR. Okay, so I think the special case of this optimized OCE, a special case of this OCE is a very popular conditional value at risk. Okay, so conditional value at risk is a special case of this. But then instead of just talking the conditional value at risk, measures the tail end, a one-sided tail end. Okay, now why is that? Why just this side? For example, if you do regression, if you do this, then I'm talking about the excess. Okay, so the over is a one-sided error. What about the other side? Right, and then maybe I should just try to ignore, right, all those samples that are outside both ranges. Okay, Professor Tita, you use this a lot, right? So we refer to your Akiko. So this leads to a concept of interval CVAR. Okay, so here's a definition of the interval CVAR, and I want to point out that the C-bar is only one-sided, but that if you want to exclude the samples that are on both ends and want to focus only on this area in the middle, then you get into this notion, this quantity of interval C-bar. Okay, so the interval C-bar is basically, I'm interested only in that region between two vars, and it happens to be equal to the difference of two C-bars. This is the interval C-bar. So now by using this interval C-bar, I can pay attention to the two tails and not just one tail. Okay? Now, this interval C-bar, I know C-bar is given by this. So when you substitute this, then you get what you get for the interval C-bar is the difference of two stochastic value functions. Difference of two. The interval C-bar allows you to look at risk in the middle part, taking away the two ends. And it's not one-sided. It becomes two-sided, right? So that's a picture. And then now this leads into my two problems. And now after this page, I will stop. Is the more generally, so I've given you sort of stochastic value function here, difference of two stochastic value functions. In this case, those two value functions correspond to C-bar. But now you have difference of two C-bars, right? So more generally, you can talk about a stochastic value function in general. So this is just one realization. Okay, so outside of this, I'm going to take expectation. That's the so now your value function here, you have the random realization, and now I'm going to look at this as a function x. It's a value function because I need to minimize over y. That would give me the x. Okay, this value function is not convex, is not concave, but is what we call the implicitly convex concave. Is that if you fix one variable, if you lift this function, you see the x here. Okay, you see the x, the first level variable in the objective and the constraints. In standard stochastic programming, in particular, stochastic linear programming, this is what you see. You see the x in the constraints, but you do not see the x in the objective. Okay, this is the kind of value function in standard linear programming recourse function. Your decision variable appears, your first level decision variable appears only in the constraints, but that first level decision variable does not appear in the objective. That's a standard, decades-long stochastic programming. Why is that? Why do people not consider the case when you have an x also in the objective of the recourse function? Why is that? The reason, to me, is that when you include the objective, when you include the first decision variable in the second stage objective, immediately as a function of x, it's not convex. So if you look at this function here, whenever you have x here, typically this value function is not going to be convex. Okay, so let's take a break. I'm only half of this, so I'm going to talk about the first lecture. No time to talk about the change constraint. Okay, so I'm going to talk about this paper. Or why do you want me to talk about change constraints? Up to you. Okay, so it's already past 10:15, so I should stop. Okay, so thank you.